The term light-in-flight imaging refers to video-like data with a temporal resolution high enough to capture the propagation of light in a scene. Here we see a light front moving over a tomato in front of a wall. In a video like this, each pixel is associated with a temporal profile of light intensity, which corresponds to the amount of light that the corresponding point in the scene reflects or emits towards the camera at a given point in time. This data has been recorded using a street camera, which offers very high temporal resolution but is also expensive and limited to a single line of pixels. A cheaper alternative technology for capturing light-in-flight images are SPAD sensor arrays, which in turn suffer from low spatial resolution and often very low fill factor. To combat these drawbacks, we propose a SPAD-CCD sensor fusion approach. We use a low spatial resolution SPAD measurement with temporal resolution T and combine it with a high resolution intensity image from a CCD camera. We then aim to fuse these two images into a single data cube that has the temporal resolution of the SPAD and the spatial resolution of the CCD image. In our proposed setup, we illuminate a scene with a pulsed laser and view the scene through a single objective lens that projects the image onto a CCD and a SPAD sensor. Note that the SPAD sensor is moved slightly out of focus. We do this because our SPAD sensor has a fill factor of only 2%. By blurring the image, we mix information from every scene point into multiple active pixel areas, so that no information is lost in the inactive area of the sensor. Using an image formation model encoded in a matrix A tau, which describes the light transport from the scene to the SPAD sensor, including the defocus blur, we can reconstruct a high-resolution light-in-flight image from our measured SPAD and CCD data by solving the following optimization problem, where XHR is the vectorized high-resolution data cube, R is the vectorized low-resolution SPAD measurement, and I is the vectorized CCD image. The first term is the data term for the SPAD image formation. The second term integrates the high-resolution data cube over the temporal dimension and enforces similarity to the captured CCD image. The third term uses a matrix K, which performs a spatial integration over the data cube, thus matching the temporal distribution of light intensity in the measurement and the reconstruction. This term enforces sparsity in the data cube, helping with robustness of the reconstruction. Finally, the last term adds a total variation prior to the optimization, which acts on the spatial dimensions of each time slice. We first tested our model on simulated scenes, which we generated using a time-of-flight renderer, which ray traces the scene and stores the time that each ray has taken to travel from the light source to the camera. With this simulated scene, it is easy to see why blurring the image before it reaches the SPAD sensor is beneficial. On the left, we see the SPAD image as seen by the low fill factor sensor when it is in focus. A lot of information is lost, while in the blurred version on the right, the information is preserved by mixing it into different pixels. This view shows the simulated light-in-flight image from different angles and projected as a simple depth map. In an in-focus measurement, holes appear in the image, especially visible at the faces of the cube. In an out-of-focus measurement, these areas become smooth again, and from this, the original scene can be reconstructed. This is what the reconstruction looks like when played as a video. The measurement is shown to scale in the center. We evaluated the performance of the reconstruction for several upsampling factors, also with noise added to the artificial measurement. As one can see, the quality degrades with higher upsampling factors, and even faster when noise is involved. However, even with upsampling factors as high as 12 by 12, meaningful results can be achieved. This video shows another simulated scene, which features strong indirect reflections between objects in the scene, emphasized here for visibility. Also here, upsampling factors of 12 by 12 are possible and yield good results. Finally, with the setup mentioned before, we captured actual measurement data to test our model in the real world. Our CCD image has a spatial resolution that is a factor of 3 by 3 higher than that of the SPAD sensor, which is a 32 by 32 pixel array. This is the full measurement of this scene, showing a section of a basketball. The reconstruction looks as follows. This is another scene showing a plastic cup filled with water in front of a slanted wall. The reconstructed image is much smoother, which is especially visible in the depth map. Finally, this scene shows a golf ball where the reconstruction is sharper and less noisy. Note how in the three-dimensional view of the reconstruction on the left, the texture of the golf ball is transferred into the light-in-flight image.